All right, diving in today, huh? We're going deep on a question that, well, it really sits at the heart of both physics and philosophy.
Yeah, that intersection, right where they meet.
It's the nature of space and motion. Are they absolute? Like, do they just exist on their own, totally separate from all the stuff, the matter within them?
Or are
Or
they relational, totally defined by how objects interact with each other?
that's the puzzle. And for you, our listener, thinking about this with your philosopher hat on, this isn't just a physics problem.
No, it goes way deeper, right? It's about the very fabric of reality itself, what's really out there.
That's what we're going to try to get at today. How does modern physics, even now, still wrestle with this question? It's ancient, but it's alive.
And to help us navigate, we're going to be looking at excerpts from the Stanford Encyclopedia of Philosophy.
Right, the entry on absolute and relational space and motion, post-Newtonian theories. It's a dense one, but it lays the groundwork.
Consider it our guide through this dense forest of ideas.
That's a good way to put it. So our mission, if you will, is to trace how these concepts have evolved. We're starting with Newton, his big ideas. Then we'll look at Mach's critiques.
Einstein's theories, of course.
Yeah.
Those revolutionized everything.
And we'll even touch on some seriously cutting-edge stuff, shape dynamics, the dynamical approach.
The philosophical arguments, those are really key here. We want to understand not just the physics, but what it means.
The implications, exactly. Be ready for some unexpected turns, because this debate, it's not settled, not by a long shot.
No, not at all. And speaking of debates, we got to start with Ernst Mach. He really shook things up after Newton came along.
Newton's absolute space, as successful as it was, scientifically,
Yeah, it explains so much.
but philosophically, it made a lot of people uncomfortable.
This idea of something so fundamental yet completely unobservable.
Absolute space. You can't see it, you can't touch it, but it supposedly governs everything.
Exactly. It left a lot of thinkers feeling, well, uneasy.
Metaphysically unsettled. And then, in 1883, boom, Mach drops his Science of Mechanics.
And that really threw a wrench into things.
Oh, yeah. What's fascinating from the philosophical side is Mach's accusation. He essentially says that Newton, in the Scholium, his famous writings about absolute space,
He violated his own rules.
his own methodology, Newton was all about sticking to observations, to what you could actually see and measure.
Right. Empirical evidence. That was his bedrock.
And Mach argued that with absolute space, Newton went beyond that. He stepped outside the bounds of what could be empirically verified.
Which, if you're committed to that kind of empiricism, it's a big deal.
It is. And this whole critique really comes to a head with Newton's bucket experiment. Our listeners might remember this one.
You spin a bucket full of water.
And the surface of the water, it curves inward. But here's the thing.
It curves before the water actually starts rotating along with the bucket.
Right. Newton argued that this curvature, it proves the water is rotating relative to something.
Something beyond the bucket itself.
Absolute space. That's his big takeaway.
But Mach, he saw it differently. He said Newton was actually arguing against what he called strict relationism.
Strict relationism, meaning?
The idea that all motion, every single bit of it, is relative to some arbitrarily chosen frame of reference. Your frame, my frame, any frame.
So Mach's point is that the bucket experiment, it doesn't disprove strict relationism entirely.
Nope. All it shows is that the water is rotating relative to the Earth, or maybe the distant stars.
So Mach's making a subtle distinction, but it's really crucial. It's not about absolute space versus any relative motion at all.
It's about what kind of relative motion is fundamental and whether we need absolute space to explain it.
Right. The nuance is key. Now, Newton had another thought experiment, besides the bucket. It involved two globes connected by a cord out in empty space.
Ah, the globes. Classic physics thought experiment.
And his point with both of these, the bucket and the globes, was to show that Descartes' view of motion, which was all about motion relative to your immediate surroundings.
It wasn't enough, especially when you're talking about rotation.
Exactly. Newton wanted to show that you could figure out if something's rotating and even in what direction without needing any external reference point.
So with the globes, he argued that you could tell if they were rotating around their center, even how fast, just by looking at the tension in the cord.
Right, and you wouldn't need anything else, no background stars, nothing. Just those two globes and the cord between them. That was his point.
A self-contained system.
But Mach, clever as he was, he had an implicit counter-argument to this. He basically asked, hold on, can you even have tension in that cord if those two globes are all alone in an empty universe?
He was questioning the very setup of the thought experiment, the underlying assumptions.
Yeah, like what would even cause that tension if there's literally nothing else in existence?
It's a really deep question. It gets at the heart of what it means for things to interact, for forces to exist.
So, from Mach's perspective, neither the bucket nor the globes definitively prove the existence of absolute space. They're suggestive, maybe, but not conclusive.
Right. They raise more questions than they answer, in a way.
They do. Now, let's dig into Mach's own ideas about inertia. We can actually break his thinking down into two main categories, Mach light and Mach heavy.
Two flavors of Mach. I like it.
So, what's the main difference? How do these two approaches tackle Newton's ideas?
Mach light is kind of like, well, it's a softer critique. More methodological, you could say.
Okay, so it's not totally rejecting Newton's absolute space.
No, not outright. It's more like, look, absolute space, it might not be strictly necessary, metaphysically speaking. We can probably replace it with something else.
And that something else being...
The frame of the distant stars.
Okay. The stars are way out there. They seem pretty fixed.
And that's actually what astronomers use as their main reference frame anyway.
So Mach light is more about a practical adjustment, not a total theoretical overhaul. But wasn't there a potential problem with this, philosophically?
Oh, definitely. You're essentially basing your fundamental laws of physics on something that seems, well, contingent. The distribution of stars.
Like, what if our universe just happened to have stars arranged this way? What if it was different?
Exactly. From a philosophical perspective, you're looking for truly universal laws. That dependence on the specifics of our cosmos feels a bit shaky.
It does. So how did Mach address that concern?
He came up with what's now known as Mach's equation. It's an attempt to connect a mass's inertia, its resistance to change in motion.
Its stubbornness about being pushed around.
Exactly, to connect that to the distribution of all the other masses in the universe.
So everything's pulling on everything else.
In a way, yeah. And the really interesting part is the weighting. The influence of a distant mass. It's not just about how much mass there is.
It's about how far away it is, too.
Exactly. More distant masses actually count for more in this equation.
Wow, okay. So in a universe like ours, with these vast, distant galaxies, this equation would basically reproduce Newton's first law.
Yeah, that's the idea. It would explain why things tend to move in straight lines at constant speeds relative to those distant stars.
The frame of the fixed stars inherits the role of Newton's absolute space.
In a way, yeah. But even Mach himself, he recognized this wasn't a perfect solution. It runs into problems in an infinite universe.
Like, if there's stuff infinitely far away, how do you even calculate its influence?
Right. And Mach also questioned whether it would hold up if those stars were all moving around really rapidly relative to each other.
So Mach light is more of a refinement than a revolution. But Mach heavy, now that sounds like the real deal.
Oh yeah, Mach heavy is a whole other beast.
Yeah.
Einstein actually gave it the name Mach's principle.
Okay, and what's the big idea there?
It's radical. It wants to build a completely new framework for mechanics. One where the only things that matter are the relative distances between objects and how those distances change over time.
So no absolute space, no pre-existing grid that everything moves against, just objects and their relationships.
Exactly. It's about generally relativistic motion.
Yeah.
Mach even wanted to get rid of absolute time, too.
Wow. Okay, so instead of saying that a force causes an object to accelerate within absolute space,
You'd say that the object's acceleration is fully determined by how its spatial relationships with every other piece of matter in the universe are changing.
it's all about relative accelerations.
Exactly. And this led Mach to some really wild speculations. Like, remember the fixed-sided bucket?
One from Newton's experiment.
Yeah. Mach said, imagine that bucket was supermassive, unbelievably heavy. He suggested that just the relative rotation between the bucket and the water might be enough to push the water outward.
Wait, even before the water starts spinning with the bucket?
Yeah, like some kind of instantaneous influence across space, just from the relative motion and the massive bucket.
That's mind-blowing.
It is. And philosophically, it's incredibly interesting because Mach compared this idea to electromagnetic induction.
So, like, how a changing magnetic field can create an electric current.
Yeah. He thought something similar should be happening with gravity. That inertia, a body's resistance to acceleration.
Is somehow a result of its interaction with all the other masses in the universe?
Right. And actually, general relativity does have something kind of like this called gravitomagnetic induction. The Gravity Probe B mission even detected it.
Wow, so there's a real physical phenomenon that echoes this Mach-heavy thinking.
There is. But for it to fully work, for it to reproduce all of Newtonian physics in a Mach-heavy way,
Hmm.
well, this connection between inertia and the rest of the universe's matter, it would have to decrease with distance much slower than gravity does.
So there are still some puzzles to work out there.
Definitely. But if a true Mach-heavy theory could be found, it would be a huge win for strict relationism. It would wipe absolute motion off the map entirely.
That would be a pretty profound shift in our understanding of the universe.
No doubt. But realizing Mach-heavy within the framework of classical physics, that proved to be a real sticking point.
Like it couldn't quite get there.
Yeah, people tried, Mach himself tried, but a fully consistent classical theory that embodied all the ideas of Mach-heavy, it just never
It
materialized.
needed a new kind of physics.
It did. And that's where Einstein comes in. His theories of relativity changed everything.
Okay, so special relativity, or STR as we'll call it, it's famous for being based on a principle of relativity, but you said it's a special kind of relativity.
Right. It's important to understand what that means.
So how does this special relativity play into the whole absolute versus relational motion debate?
Well, the principle of relativity in STR is actually the same one that's at the heart of Newtonian physics, the Galilean principle.
Which says,
There's no preferred standard of velocity, no cosmic speedometer that tells you your true speed.
so whether you're at rest or moving at a constant speed, it all depends on your frame of reference.
Exactly. But here's the thing. Whether a body is accelerating or rotating, that's still an absolute fact within STR. It's not relative.
Okay, so in that sense, STR doesn't really change the game that much compared to Newtonian physics.
In terms of absolute versus relative motion in mechanics, no, not really.
But there's an argument to be made that STR introduces a new way of thinking about relationalism altogether.
Oh, absolutely. This is where it gets really interesting philosophically.
So instead of just looking at the relative positions of objects at a given time,
STR shifts the focus to the relationships themselves within the fabric of space-time.
space-time, that's Einstein's big contribution, right? The merging of space and time into a unified entity.
Exactly. And thinkers like Dorling and Maudlin, they really ran with this. They argued that the invariant relationships between events in space-time.
Invariant meaning they're the same for all observers, no matter their relative motion.
Right. They argued that these invariant relationships, specifically the space-time interval, they become the key to understanding a body's state of motion.
Okay, so for our listener who's coming at this from a philosophical angle, how do these space-time relationships in STR manage to do what classical relations couldn't?
It all comes down to how STR revolutionizes our ideas about space and time themselves. Things like length contraction, time dilation, the relativity of simultaneity.
Yeah, those are some of the mind-bending consequences of STR.
They show us that the classical starting point for relationalism, the idea of looking at relative distances between objects at a single instant in time, it's no longer a valid objective concept.
Because what constitutes a single moment becomes relative itself.
Right. It depends on your frame of reference. So that basic assumption of classical relationalism, it crumbles in the face of STR.
Okay, so that throws a wrench in things. But then how do you build a relational account of motion in this new relativistic world?
Well, that's where the space-time interval comes in. It's a quantity that combines spatial and temporal distances, and it's invariant. It's the same for everyone.
So it's a solid foundation to build on.
Exactly. And if you think about the network of space-time intervals connecting all the bits of matter in a system, you start to see how rotation and acceleration leave unique fingerprints.
Okay, give me an example.
Take the spinning bucket again. In SCR, the space-time interval between a water molecule at the edge at one moment and then itself a moment later. That interval will be different from the interval for a molecule near the center.
Because the edge molecule is moving faster, so it's covering more spatial distance in that same amount of time.
Exactly. So the act of rotating, it changes the space-time relationships within the object itself across time.
It's not just about the relationships between different objects anymore. It's about the relationships within an object over its own history.
You got it. You can't make something rotate or accelerate without altering those space-time intervals within it.
So, in a way, facts about rotation and acceleration, they become encoded in these space-time relationships.
Precisely. It seems like a big win for relationalism, conceptually speaking.
But you said it might not fully satisfy someone like Mach or Leibniz.
Right. The problem is the space-time intervals, they're not just spatial distances. They mix space and time together.
So it's not the pure spatial configuration that classical relationalists were after?
No. And another issue is, While SDR gets rid of absolute velocity, absolute accelerations and rotations, they're still there.
They're still absolute, not relative.
Yeah. And they're linked to a body's space-time intervals with itself, its own past and future, not just its relations with other stuff in the universe.
So it's a victory for relationalism, but with some big asterisks.
Exactly. Now, SDR didn't include gravity. And the way gravity worked in Newton's theory, that instantaneous action at a distance.
Yeah, that clashed with STR, right? With the speed of light being a cosmic speed limit and no absolute simultaneity.
Big time. And that led Einstein to general relativity, or GTR. And initially, he had even bigger hopes for GTR.
He thought it would fully relativize motion, even acceleration.
That was his goal. From 1907 onwards, he was obsessed with this idea of relativizing acceleration to get rid of absolute motion once and for all.
And his big insight was the equivalence principle.
The equivalence principle. You know, the thought experiment with the rocket ship.
Classic Einstein.
You're in a rocket, accelerating uniformly through empty space, and then you're standing still on Earth in a gravitational field.
And locally, you can't tell the difference. The sensations are the same.
Exactly. That's the core idea.
Yeah.
And it led Einstein to pursue something called general covariance,
Which means
writing the laws of physics in a mathematical language that works no matter what coordinate system you're using.
so no matter how you're moving, no matter your frame of reference, the laws look the same.
Right. He believed that if he could achieve this, it would mean motion is truly relative. There would be no special privileged frames of reference that suggest some kind of absolute motion.
And he got there, right. In 1915, GTR achieved this general covariance.
A monumental intellectual feat. But, as you said, most physicists today, they don't think GTR completely eliminated absolute motion.
Even though that was Einstein's hope.
Yeah. It turns out there's some real complexities in GTR, some things that make you question whether motion is fully relative.
Like what?
One big thing is the existence of empty space solutions in GPR. Take Minkowski spacetime, for example. That's the spacetime of STR.
The flat, unchanging spacetime.
Right. And in GTR, even if you imagine taking away all the matter and energy in the universe, gravity doesn't just disappear. Spacetime is still there. It has its own structure, its own dynamics.
So spacetime can exist even without anything in it.
According to GTR, yeah. And that's a problem for a strong Machian view. If spacetime is fundamentally defined by matter, how can it exist when there's no matter around?
It's like saying the stage can exist without any actors, without any play being performed on it.
Yeah, it makes you wonder, what's the stage made of then? What gives it its structure?
Right. If it's not the matter, then what is it? That's a big question for relationalists.
Absolutely. Another point is that GTR lets you model a single rotating object all alone in an empty universe.
But wait, doesn't rotation require a reference frame? Like you need something to compare it to?
That's the Machian argument. And for a strict Machian, that scenario would be impossible. You can't have rotation without something else to define it against.
But GTR allows it.
Yeah. The way it's usually understood is that the rotation is relative to some background spacetime. The object's presence curves this background, but the background is still there.
So even though spacetime in GTR is dynamic, it's still acting like a kind of stage, isn't it? A stage that motion can be defined against, even if the stage itself can bend and warp.
That's one way to interpret it, and it's definitely a point of philosophical contention. Now, there's another criticism of GTR. People sometimes say that it's metric, the mathematical tool it uses to describe spacetime.
Yeah, the metric.
They say that the metric inherently distinguishes between absolute acceleration and rotation.
Meaning it treats them as absolute, not relative.
Yeah. And technically that's true. But it's a bit of an oversimplification to say that GTR, therefore, fails the test of Leibnizian relativity of motion.
Why is that?
Because the way the metric works, the local inertial structure that defines, is not just some arbitrary pre-existing thing. It's determined by the distribution of matter and energy in the universe.
So the matter shapes the metric, and the metric then governs how things move.
In a nutshell, yeah. And even Einstein himself, he realized by 1918 that GTR, in its original form, didn't fully live up to what he hoped it would be in terms of Mach's principle.
It didn't fully satisfy the Mach-heavy vision.
No. But GTR does have some features that are, well, surprisingly Mach-friendly.
Oh, like what?
One big one is frame dragging.
Frame dragging, what's that?
It's the prediction that a rotating mass will actually drag space-time along with it, like twist it a little bit.
So, like, imagine stirring a pot of sick honey. The honey near the spoon spins with it, but even the honey farther away gets pulled along a bit.
That's a good analogy. And it's kind of similar to Moss' idea with the rotating thick-sided bucket.
Right, where the massive bucket might influence the water inside even before they're both spinning together.
Exactly. And there's this really cool thought experiment done by Brill and Cohen. They imagined a massive, rotating spherical shell.
Like a giant spinning hollow ball.
Yeah. And they showed that inside this shell, the frame dragging would become so strong that it would completely eliminate the original flat Minkowski background spacetime.
Whoa, so inside the shell, space-time would be totally determined by the spinning matter of the shell itself?
That's the idea. It's a very Mach-heavy scenario. And it's not just theoretical. Some of our cosmological models, the ones that describe the universe as a whole, they suggest something similar might be happening on the largest scales.
So the way inertia works here on Earth might be influenced by the distribution of matter across the entire universe.
It's a possibility that's being actively researched. And GTR has this other really unique feature. It doesn't have a fixed prior space-time structure built into its core equations.
It's not like Newtonian mechanics, where you have absolute space and time as a given.
Right, and it's not even like STR, which, even though it introduces space-time, it still treats it as this fixed, unchanging background.
But in GTR, space-time is dynamic, it evolves.
And this leads to a lot of debate about what's called background independence, whether GTR is truly background independent or whether there's still some kind of hidden background looking beneath the surface. It's a hot topic in both physics and philosophy of physics.
So where does that leave us?
In a strange place. We have these solutions in GTR that seem to imply absolute motion is still a thing. But then we have other solutions, especially the ones that describe our actual universe, that suggest motion might be entirely relative after all.
And even if it turns out that motion is relative, the bigger question of whether space-time itself is a fundamental substance or just a network of relationships.
That debate rages on.
It does. It's fascinating.
Yeah.
Okay, let's shift gears a bit and talk about some of the more recent attempts to tackle this whole absolute relative debate. Starting with shape dynamics, it's presented as a modern effort to truly realize that Mach-heavy vision that we talked about earlier.
Yeah, shape dynamics is pretty wild stuff.
So where does it begin? What's the basic starting point?
It's spearheaded by these physicists, Barber and Bertotti. And their approach is really different. They're not just trying to tweak gravitational theories within a pre-existing space-time framework.
Okay, so they're going deeper.
Much deeper. They want to reconstruct the very foundations of mechanics. But they want to do it using only relational quantities.
Relational quantities, meaning?
Things like the distances between particles, the relative velocities, all the stuff that describes how objects are related to each other, but not their absolute positions or motions.
So they're throwing out absolute space and time right from the start.
Exactly. It's a really ambitious project.
It sounds like it. Now, for our listener who might not be super familiar with the technical details of mechanics, can you give us a bit of an intuitive picture of how shape dynamics actually works?
Sure. Think of it like this. In physics, we have this really powerful tool called Lagrangian mechanics. It's a way to describe how systems evolve over time by focusing on energy rather than forces.
Okay, so instead of thinking about pushes and pulls,
you think about energy, potentials, and how systems tend to move in ways that minimize their energy.
Right, like a ball rolling down a hill. It takes the path of least resistance, the path that minimizes its potential energy.
Exactly. Now, shape dynamics wants to rewrite these energy-based descriptions, these Lagrangian formulations, but using only those relational quantities we talked about.
So no absolute positions, no absolute velocities, just the relationships between objects.
Right. They're essentially focusing on the shape of the system, the intrinsic arrangement of its parts.
The shape, but not the size, or the orientation, or where it is in space overall.
You got it. They're trying to build a theory where only those intrinsic relational aspects of the universe are physically meaningful. And they even try to tackle time itself in this way.
Time, too.
Yeah, they want to derive a notion of time from the dynamics on this shape space, this space of all possible shapes the universe can have. It's what they call emergent temporality.
Whoa, so time itself would emerge from the evolution of the universe's shape.
That's the big idea. It's heady stuff.
It is. So how do they actually get the laws of motion, the equations that describe how this shape evolves? It sounds technically challenging.
Oh, it is. This is where the concept of best matching comes in.
Best matching.
The basic idea is to use the similarity group,
Which is?
the set of mathematical transformations that correspond to translations, rotations, and dilations. Basically, moving the system around, rotating it, or changing its size.
Okay, I'm following so far.
So you have these possible histories of the universe,
Yeah.
each one a sequence of shapes changing over time, and you want to find the best history, the one that makes the most sense physically.
And how do you do that?
By using those transformations, those elements of the similarity group, to minimize the intrinsic differences between successive shapes in the sequence.
So, like, imagine a triangle. It can move around, rotate, change size, but its basic triangular shape is still there.
Right. And best matching allows you to essentially align those different versions of the triangle, to factor out the irrelevant stuff and focus only on the changes in its shape.
So you're isolating the essential intrinsic changes in shape, regardless of its position, size, or orientation.
Exactly. And this process, it naturally induces a metric on shape space,
A metric.
a way to measure distances and define geometry. And once you have a metric, you can write down dynamical laws, equations that describe how the shape evolves over time.
Wow, so you're building a whole new kind of physics from the ground up based on these purely relational concepts.
That's the goal of shape dynamics. And the really cool part is this best matching idea, it can be extended to general relativity too.
Really? So you can do shape dynamics in the context of Einstein's theory.
You can. It's called relativistic best matching. And it leads to a version of shape dynamics that's compatible with GTR.
So how does that work? How do you apply this to GTR?
Well, GTR uses this thing called the 3+1 formalism. It's a way of slicing space-time up into a series of three-dimensional spaces, each one representing a moment in time.
Okay, so you're picturing space-time as a stack of snapshots, each one a 3D space.
Right. And in relativistic best matching, you define a shape space for these three geometries. Two geometries are considered equivalent if you can transform one into the other using diffeomorphisms and local rescalings.
Diffeomorphisms are.
General coordinate transformations. Basically, smooth, continuous changes in how you label points in space.
So like stretching a rubber sheet without tearing it.
Yeah, that's a good visual. And local rescalings, those are just changes in the overall scale of the geometry at different points.
Okay, so you're grouping together geometries that are basically the same shape, even if they're stretched, distorted, or rescaled.
Exactly. And this gives you a relativistic shape space. And what's really interesting is the trade-off it makes with GTR.
A trade-off?
Yeah, shape dynamics, it keeps absolute simultaneity, meaning there's a universal now that everyone agrees on, but it treats overall scales as relative.
Whereas in GTR, you have the relativity of simultaneity, but scales are treated as more absolute.
Right. It's a profound difference in how they picture the fundamental structure of space-time.
It is. So from a philosophical perspective, what are some of the key takeaways from shape dynamics? How does it compare to Newtonian mechanics and GTR?
One interesting difference is in the structure of their solution spaces. The solution space of a theory is, well, it's the set of all possible ways the universe can evolve according to that theory.
Okay, so like all the different paths a ball could take rolling down a hill.
Kind of, yeah. And the best matched Newtonian theory, it actually has a solution space that's a subset of regular Newtonian mechanics.
Meaning?
It only includes solutions that also satisfy certain additional constraints. For example, it only allows universes where the total angular momentum is zero.
So it's more restrictive.
In a way, yeah.
Uh,
And some people see that as a good thing, as like shape dynamics explains why we observe this conservation of angular momentum, whereas in regular Newtonian mechanics, it's just kind of assumed.
okay, so it potentially has more explanatory power.
Maybe. But with GTR and shape dynamics, their solution spaces overlap, but neither is a subset of the other.
So it's not clear that one is better than the other in terms of what it allows or predicts.
Right, it's more complex than that. And as for the philosophical motivations behind shape dynamics, well, eliminating absolute quantities, that's definitely a big one.
Getting rid of absolute space and time, making everything relational.
Exactly. But Barber, one of the main guys behind it, he also puts forward this empiricist argument.
Empiricism meaning.
The idea that our knowledge should be based on observation. And Barber says that the only things we can truly observe directly are angles.
Angles.
Yeah. Like you can directly compare the angle between two stars to the angle between your fingers.
I see.
But you can't directly observe distances or time intervals without making assumptions about how your measuring tools work.
So Barber thinks our fundamental physics should be built up from angles.
That's his argument. But it's been criticized, you know. People have pointed out that even measuring angles, it's not as straightforward as it seems. You still need assumptions about how light propagates, about the geometry of space.